Okay, deep divers, you ready for this one? Today, we're diving headfirst into a cosmic mystery that'll really make you think about the universe.
And everything in it.
Yeah, buckle up, because we're talking about dark energy.
That's right, that mysterious force pushing everything in the universe farther and farther apart.
Faster and faster, too.
Like we're on this cosmic road trip, right? Cruising along and
This
suddenly.
universe just slams on the gas.
Exactly, and the biggest mystery of all.
We can't see who's driving.
Or what's fueling that engine?
Okay, so that's where dark energy comes in. But here's the thing.
It gets even weirder.
Oh, I'm ready for it.
This new research paper landed on my desk, and let me tell you, it's shaking things up.
You know how we love a good shake-up in cosmology?
This paper is titled Scant Evidence for Thawing Quintessence.
Okay, even the title sounds mysterious. Tell us more.
Well, before we jump into the deep end of thawing quintessence, we need to set the stage.
I like it set the stage.
The leading theory we have for dark energy right now is this thing called the cosmological constant.
Right, because even though we can't see dark energy, we know it's doing something right.
Exactly, and to describe what it's doing, cosmologists use a term called the equation of state.
Okay, so the equation of state helps us figure out if dark energy is more like a gentle breeze or like a...
A raging hurricane.
Exactly right.
So the cosmological constant in this case would be like setting that cosmic cruise control.
It means the universe is expanding, sure, but the energy driving that expansion, that cruise control,
It stays the same,
which would be fine, except
except this new research is saying, hold on a minute,
I knew there had to be a twist.
they're digging into something called thawing quintessence.
Okay, before we go any further, I need a little help picturing this. What is thawing quintessence?
Imagine instead of a steady cruise control,
Yeah.
the energy behind the universe's expansion is more like a dial.
Okay, a dial, so you can like crank it up or down.
Exactly, it can be adjusted over time.
So are we saying dark energy could be...
Hitting the gas or maybe even tapping the brakes a little.
Whoa. Okay, this is where it gets really interesting.
It does, and here's where things get even more wild. There are different types of this thawing quintessence.
Different types,
Well,
like
there-
flavors?
You got it. Each flavor has its own way of changing over cosmic time.
Okay, cosmic flavors.
Yeah.
I'm intrigued what makes these flavors different.
Think of it like this. Each flavor is like a different setting on that cosmic dial we talked about.
Got it.
Some might make the quintessence field change really fast,
Oh.
while others would make it change slowly, like molasses in January.
Molasses in January.
The
I love it. So in this research paper, they're looking at
two main flavors, and they're differentiated by something called effective mass.
effective mass. Okay, things are getting a little complicated for my taste. Can you break that down for us?
Absolutely. Imagine you're pushing a shopping cart.
Okay.
If that cart's full of feathers, it'd be super easy to get it moving fast, right?
I practically float away.
Exactly. That's a small, effective mass. Now imagine that cart's full of bowling balls.
Oh my goodness. I can barely even push that to the checkout.
Exactly. It's much harder to get going and change its direction, which
They
means
have a large effective mass.
you got it.
Yeah.
Now, some flavors of this quintessence, they have a high effective mass, like those bowling balls. They're slow to change.
And others.
Others have a low effective mass, more like your feather part, changing rapidly.
Okay, I think I'm following this. So we've got our cosmological constant, our steady cruise control, and then thawing quintessence, this adjustable dial. And each flavor influences how fast it can change.
Precisely.
But how did the researchers actually figure out which model fits our universe better? Did they just like put on their lab coats and whip up some dark energy in a test tube?
Not quite, but they did something even cooler. They used computer simulations to test these ideas.
Simulations? Are we talking like the Matrix here?
Even bigger, they created a whole bunch of simulated universes, each one with its own unique flavor of thawing quintessence.
Okay, so like a cosmic buffet of universes.
Exactly, and then they had to see if any of those simulated universes matched up with...
With what we actually observe in our own universe.
Yeah, you got it. It's like trying to find a cosmic twin.
And how do you go about finding a universe's twin?
Well, you need data, lots of it. They focus on three main sources that astronomers use to measure the universe's expansion.
Okay, hit me with the data.
First up, we have DSI, the Dark Energy Spectroscopic Instrument.
Okay, I've heard of DSI.
It's making a detailed 3D map of the universe by measuring the light from millions of galaxies.
So it's like a cosmic cartographer.
Exactly. And this map helps us see how the universe's expansion has changed over billions of years.
Okay, that's one source of data. What else?
Next, we have Pantheon, plus a massive collection of observations of supernova explosions.
Supernovae, as in exploding stars.
The most powerful explosions in the universe. And here's why they're important. Type E a supernovae. They always explode with the same brightness,
Really? So every time one of those goes, boom, it's like the same amount of light.
almost like a cosmic light bulb. And because we know how bright they should be,
We can tell how far away they are.
exactly, they become like cosmic mile markers, helping us measure the expansion of the universe across vast distances.
That's amazing. They're using exploding stars to measure the universe. It's like something out of Star Trek.
And then there's one more piece of the puzzle, a source of data that takes us way back to the very beginning.
The very beginning. As in the Big Bang.
You got it. We're talking about the cosmic microwave background, or CMB for short.
Right. The CMB is like the faint afterglow of the Big Bang.
It's like the universe's baby picture, and just like how a baby picture can tell us something about a person,
The CMB can tell us about the early universe.
and how it's expanded over time.
Okay, so we've got DSI mapping galaxies, Pantheon Plus using exploding stars, and the CMB giving us a glimpse of the universe's infancy.
3 powerful tools for probing the mysteries of dark energy.
But with all that data, how did they even begin to make sense of it all?
Well, they use some really advanced statistical techniques to essentially create a cosmic fingerprint.
A fingerprint for each of their simulated universes.
Exactly. And then they compared those fingerprints to the one we see in our own universe.
Looking for a match.
A cosmic match made in the data heavens.
Okay, so did they find a match? Was any of the Thawing Quintessence universes a perfect fit?
That is the million-dollar question, isn't it? And the answer is, well, it's complicated.
Uh-oh, I don't like the sound of that. What do you mean complicated?
Complicated in the best way possible. The researchers, they were able to make simulated universes that kind of looked like ours.
Kinda, but not a perfect match.
Not exactly. Remember how we talked about the equation of state for dark energy? It tells us how dark energy behaves, whether it's constant or changing.
Right, like comparing it to a gentle breeze or a raging hurricane.
Exactly. Well, the simulations using Thawing Quintessence, they could get kind of close to the equation of state we observe.
But not close enough to be like, Eureka, we found it.
Not quite. And that's where things get really interesting, because it could mean a few things.
Okay, lay it on me. What could it mean?
Well, it could mean that maybe our observations are just not precise enough yet.
You're saying our instruments, our telescopes, they're not quite powerful enough to give us the definitive answer.
It's possible. Or it could be that thawing quintessence is just not the right explanation.
So back to the drawing board for dark energy.
Not so fast. There's another possibility, and this is where it gets really mind-bending.
Okay, I'm always up for a good mind-bending cosmology puzzle.
What if dark energy is even more complex than we've imagined?
Okay, you're really going to have to walk me through this one.
Imagine this. What if dark energy isn't just one thing, but it's like a combination of things?
Like a cosmic cocktail.
Exactly. Maybe it's part cosmological, constant, part thawing, quintessence, or even something entirely different that we haven't even thought of yet.
Whoa, okay, so you're saying dark energy could be a blend, a mix of different components,
Yeah.
each with its own set of properties and behaviors.
Exactly. And those components, they might interact with each other in ways we don't fully understand.
Okay, I'm starting to get a headache just thinking about it, but in a good way.
Hmm.
So if dark energy is this complex, multifaceted thing, how do we even begin to study it?
That's the challenge, isn't it? And it's why this research is so important. Even though it didn't give us all the answers, it's opened up new avenues for exploration.
So where do we go from here? What's the next step in this cosmic investigation?
More data. We need even more precise measurements of the universe's expansion, and that's where future telescopes like the Nancy Grace Roman Space Telescope come in.
Right, the Roman Space Telescope. It's like the Hubble Space Telescope's even more powerful successor.
Exactly. It's going to revolutionize our understanding of dark energy by giving us the most detailed maps of the universe we've ever seen.
And with those maps, we might finally be able to unravel the mysteries of this elusive force.
And maybe even catch a glimpse of what the future holds for our universe.
A universe filled with dark energy, a cosmic force we can't see or fully understand. It's enough to make your head spin.
But it's also incredibly exciting because it reminds us just how much we still have to learn about the universe and our place in it.
Exactly. It's a reminder that the cosmos is full of surprises and that the journey of discovery is far from over.
And on that note, I think we've done our brains enough exercise for one day.
You got that right. Until next time, deep divers, keep those minds curious, and remember, the universe is out there waiting to be explored.